So we're going to start off talking about Igneous rocks. And you should have out your Earth Science reference table. Open up to page 6. We're going to learn how to use this chart. It's kind of complicated, many multiple steps with it, but I think by the time this lesson's over, things should make a little bit of sense. So first of all, how do we classify igneous rocks? We do it on the texture. And when I say texture, we're really referring to the size of the crystals and the mineral composition. So take a look at this image here. Here we're looking at a piece of pegmatite. Now, pegmatite has really, really big crystals. I don't know if you can see this, but this whole chunk right here, that's one big old crystal of potassium feldspar. This gray blob right here is another crystal that might be andesite. This big white blob might be a crystal of quartz. And you can see based on the size related to the penny, they're pretty big. Now, a great example of this might be something like the sand that you find at the beach. It's very light in color. It's very light in weight for its size. It has a low density. And actually, aluminum oxide is pure white. So the whiter the sand is, the more felsic it is. Now, some places on Earth are famous for having black sand beaches. There's definitely a few in the Caribbean. There's a bunch in Asia. Basically, anywhere you have a lot of geologic activity, in particular volcanoes, we find this. Because volcanoes, while they do throw out some felsic stuff, you could also definitely find some mafic things like basalt. Yeah. So let's take a quick tour of ESRT page 6. Crystal size is probably the most important, and we find that combined with texture and grain size. So textures can be glassy, fine, coarse, or very coarse. Well, glassy, basically it looks like a piece of glass. Fine, you could see the crystals, but they're smaller than 1 millimeter across. So to give you an idea, a millimeter is about the width of a dime. Coarse, and when I say width, I mean like holding it sideways on its edge. Coarse is the next step up, and that is anything from 1 millimeter to 10 millimeters. This could be the diameter of a dime from one side to the other. That's about 10 millimeters. And then anything bigger than that, if it's basically bigger than a dime in in its width, we're going to call that very coarse. And really, all of those we just call pegmatite. And again, here are those sizes. So pegmatite's a great example if it's got really, really big crystals. If they're crystals that are visible and they're about the size of, man, I'm trying to think, like little beads or smaller, then it would be granite, diorite, gabbro, or more rarely these two, peridotite and dunite, which we'll talk about at a later point. Fine, fine crystals are basically sand size crystals, very, very small crystals. And then if it's smaller than that, it's glassy. And it basically, you really don't see the crystals individualized, and it just like looks like one uniform blob. So key fact is igneous rocks have intergrown crystals. I don't know if you can see, but these black crystals are growing into the white crystals. These white crystals are growing in between the black crystals. They're all growing into each other. Here, the pink ones and the black ones are growing into each other. This is not intergrown. So what you're looking at here is, you can see this is like a big pebble, there's another pebble. They're kind of all glued together. So I could see that these individual pebbles lived a former life. They were their own thing, and then at some point they got glued together. So our next step is, where was it formed? So if it was formed outside the volcano, we call that extrusive. This is from yesterday. This is not new information. Out of the volcano is extrusive, and these are all shot out of the volcano. Intrusive means it formed inside the earth. So all those on the bottom, those were formed underground and at some point got pushed up to the surface. Does it have bubbles? If it does, we call it vesicular. Again, another vocabulary term from yesterday. And also, vesicular might sound familiar if you've ever taken living environment. Uh, you might have heard the term vesicles inside a cell. They're little bubbles in the cell. Well, we got the same thing here, little bubbles. And this is where they are. So if you're anywhere in this category, you're going to find little bubbles. You'll notice that those little holes, those little gas holes, they're only found in extrusive rocks, only found in volcanic rocks. So just like when you open up a 2-liter soda bottle, sometimes the foam bubbles up and comes out. Well, that's the same idea. When you open up a bottle of soda, you're reducing the pressure that's inside there. And those gas bubbles want to come out of solution. Well, when you have lava that's deep inside the earth, as in the form of magma, when it comes up to the surface, there's less pressure. So guess what wants to come out of the solution? Bubbles, right? So carbon dioxide gas, oxygen, nitrogen wants to come out, and they make these little microscopic, or even sometimes bigger, bubbles that give the appearance of the rock. It looks very porous. It looks like a sponge almost. And in fact, some of them, like pumice, are so low density they could float on water. We'll take a look at that tomorrow. If there are no bubbles or no gas holes, we call that vesicular. And that's everything in these sections. So these should be smooth and have no bubbles. Color. If we move to the left on the chart, it'll be very light in color. And as we progress across, it gets darker and darker till we get to the extreme right where they're darkest. These guys are basically black. These guys are basically white. Density is our next one. It's low density on the left. It feels light in your hand. And on the right, we have high density. So it feels very heavy for its size. So the process of identifying the rock is not too hard. You just got to know the traits and line up the columns. So unless you have any other information regarding this rock, like you don't see that it's like super, super light or it's darker, stick with the middle. So right in the middle of the word rhyolite, because this is going to be the example we use, we're going to draw a line straight down. Now you don't do this on your own copy. I'm just showing you this as an example. As you go down from rhyolite, you're going to see this whole section of minerals down here. Now you'll notice the red line intersects each of these sections. So for example, potassium feldspar, quartz, plagioclase feldspar, biotite, and amphibole, those all make up a certain percentage of the rock. And if you were to take a sheet of paper, lay it across that, and mark off each of the sections, you could estimate how much of each mineral is in your rhyolite. So rhyolite might be made up of 25% potassium feldspar. It might be made up of 40% quartz, and so on. All right? We're going to take a look at that tomorrow, but it's a great use of this tool where we could find out what minerals are in each rock. So let's do a little bit of practice. Let's name a light-colored, fine-grained rock that has no bubbles. I don't know if you could read that, but it's rhyolite. Yeah, let's try another one. Coarse-grained, dense rock. It would have to be gabbro. Now, if I said very dense rock, you would be in this section here. These are relatively uncommon, though. We're going to find that about peridotite and dunite. Okay, and I want you to try and do this one yourself. Name a very light, glassy, extrusive rock that contains bubbles. So light colored would be there. Glassy would be these. Extrusive with bubbles. Bubbles means vesicular. It would be there. So yeah, our answer would be pumice. All right, I'm going to skip the exit slip for now.